recording. And if you can share your screen, and we'll go from there.
Right.
And feel free to introduce yourselves as you go.
All right. See.
What is this high-tech technology right now?
Share.
We're using
Okay.
2 different laptops.
Oh,
Let me see. Screen 2. Okay. Share.
looks like it's happening. There it is. I see it.
Okay, perfect.
All right. That's perfect.
That's a great logo. Wow.
Thank you.
All right. So welcome. My name is Carlos Munoz. I am a student at NJIT, and my colleague here is Dariel Torres.
Hello.
And we are here to pretty much explain to you our new and improved design, I guess, of the Arrow mission, Aerospace Retrieval and Reentry Observation Workstation. And without further ado, let's meet who Arrow is. So, what is our mission? Arrow is a multi-instrument re-entry experiment that consists of 2 payload systems, one stationary payload named Overwatch and a deployable payload named Scout. Overwatch's primary focus is to house, transport, and deploy Scout as it travels on the sounding rocket, as well as receive and collect data throughout the entire mission. Once, oh, sorry. You want to go?
Oh yeah. Once Scout is deployed, it will transmit data back either to the Overwatch or to the Iridium constellation of satellites using the rock block system. And then through there, we can look at all the data that we gather from the Scout after it's deployed. And we'll go over the main purposes of Scout and Overwatch in a bit.
Why is Arrow in space? Arrow's mission requires a suborbital flight that the experiment is designed for a scientific study. It requires suborbital flight because it's an atmospheric reentry that cannot be replicated or accurately simulated on Earth's ground. In short, Arrow goes to space because science demands it. Only by flying through the reentry atmosphere we can truly understand the environment we're studying.
Yes. So it is in space mostly because we have a lot of different sensors that will measure. One of the biggest sensors we have is a Langmuir probe, is to measure electron density. And what we're trying to do is measure the electron density as we are re-entering the Earth's atmosphere. Since we're starting at about 100 to 170 kilometers high, we want to gather the electron density throughout the atmosphere while going down.
This mission objective 1, our Arrow mission overview. The main purpose of Overwatch is Scout's Guardian, central hub. We will protect our Scout using Overwatch. We'll have an automated deployment system using a spring-loaded rail system with a multi-point cam holding Scout throughout the launch to reduce any vibration or harsh turbulence as we get to apogee. Once we're there, Scout will then be deployed by Overwatch, and now we commence phase 2 of our mission. And on the right, there is a little description, visual description of what the mission overview is like. So we have the events from RockSat launch all the way to the apogee, and the ejection would happen around 155 kilometers. And as soon as it's ejected, we're going to be live transmitting data in seconds. And as it re-enters Earth, we're going to be collecting electron density, the dynamic forces exerted on the payload, and harsh environmental conditions until a touchdown. Next slide.
And then on to mission objective 2. Mission objective 2 is the collection of data and transmission of data back to either the Overwatch or to ourselves so that we can actually look at it because it's deploying out of it. We're not sure if we're able to really recover it or if there's a way to recover the deployable. So it'll really consist of let's see.
So we're using a
Yeah.
two-way system for data transmission. One will be using an RF transmitter that reaches about 50 kilometers. And in interval sections, we will be sending live telemetry system data from the Langmuir probe or various sensors within the Scout. During this intervention of transmitting data, we also have an SD card on board both Overwatch and on Scout for redundancy to make sure we can actually recover most of our data, if not all of our data. We're intending to use a rock block system where it's connected to the Iridium constellation satellites to receive and store data as a backup plan. As of right now, we don't know the parameters if we are allowed to use a rock block system. Just in case we're not, we will be using an RF transmitter to transmit information.
Yeah. That's what we, and at the very end, in the conclusions for the questions and stuff, we have if we can really use the rock block. We've seen other teams use it, especially during the presentation we saw last year. So, yeah. Okay, and then move on to mission objective 3. Mission objective 3 is to stabilize the deployable. We will be doing this by using aero fins, and this will just create a stable flight for better data collection. We don't want the scouts tumbling, going, spinning, and everything. We don't want to messing with the electron density measurements or the barometric pressure density like test. Then for recovery, we want to recover scout possibly. So we will use a parachute to slow the descent down once we reach an altitude. And then we're thinking maybe using a GPS module to see if we can track its location. And we understand that's probably gonna land out way far in the ocean, so we want to use like possibly like high visibility paint, maybe strobe lights, and so like if any passing by ships will see it, like, or they can pick it up, or it'll be like a note in a bottle type thing where it just lands in the ocean, just washes up on shore. We'll engrave onto the side of Scout our name and address and where they can find us. So in case anybody does find it, they can give it back to us, and so hopefully we can take the SD card out and retrieve all the data. But then we'll have multiple points of data retrieval, including the rock block.
As
In
for
case there's
oh,
any
sorry,
problem. Yeah,
back
go
one.
ahead. Oh,
Go back
oh.
one. We also mission objective 3 also includes the post mission analysis. Once all the data is collected, we're teaming up with the physics students who are involved in the Center of Solar Terrestrial Research to process all the data collected and kind of analyze it with them. They are working in this research with Dr. Human. And this is like very useful benefit information for them. Having live data that has been recently recovered would be really nice for them to look at and help us analyze all this data collected.
Yeah, as we understand, the ionosphere is constantly changing, and if we find any anomalies or anything interesting, it'll be beneficial to them. Then we go on to concept of operations. Here at this concept of operations, we'll use time event 1 at T minus 100 for when the rocket powers on. We would like to power on all of our systems to start collecting data so we get like a nice base point. Instead of at the rock on launch, it started collecting data pretty much like a millisecond after it launched with the G-force launcher thingy. We want to do like data while it stopped so we can get that full dynamic uh, data collection. Then at about T plus 198 at apogee, we would like to use time event 2 to deploy said scout out into the atmosphere. And then at very end there at T plus 500, we believe would be the correct time to deploy the parachute for scout. That is about the same time that the sounding rocket will deploy its parachute. So we're thinking that's a pretty good time to deploy the parachute. And then
so we wanted to make this very simple. We didn't want to have too many systems going on and off throughout the uh, actual rocket launch and mission in its entirety. I feel like less moving parts is better. So we wanted to turn on at one point and turn off as soon as the battery dies completely, which would be at the end of splashdown or at the end of recovery, um, and just have it on completely until the end of the recovery section. Oh. So why space? Arrow's mission is very beneficial experiment, but why? Do you ever notice when your car radio feed cuts off randomly or you lose signal on a Google map? Well, this effect comes from electron density in our atmosphere. Electron density creates disturbance in our communications and navigation system all the time. So launching Arrow would definitely give us a better understanding of electron density in the ionosphere, which then eventually helps us advance in our communication system and navigation system as well. And every atmospheric reentry is different. We're never going to have the same um, material decay or plasma sheath that is created around any deployable reentry system. So having that, I guess, opportunity to collect that information is always beneficial for not only us but everyone else as well.
Now we move on to the Overwatch capsule architecture. So Overwatch, which is the main payload, you would say, it stays on the sounding rocket. It gets permanently mounted to the Carol system that you guys are using, and it'll house Scout. It's like a stationary hub that provides structural support and command and control. It protects the Scout payload. And then inside of Overwatch, we will have Scout, which is a smaller deployable payload designed for direct atmospheric sampling and data collection. For redundancy, we have multiple data collection systems and data storage systems. And for robust designs, we decided to make everything really heat resistant and waterproof so that we can survive re-entry and splashdown into the ocean.
Before you move on, I don't know if you noticed the red dotted lines. We strategically placed this in an area where the Carol structural lines aren't in the way of Scout when deploying. We accounted for the distance between each, um, I guess,
Each
beam.
rod
Or yeah,
spark.
yeah, and we determined the overall diameter that we can have Scout would be about 4.5 inches in diameter and about 7.5 inches in length. As for the plate, the actual capsule we'll go over it in a second. So this is Overwatch's capsule, the components layout. In the very gray, you can see the area of build. So on the outside in the dark black would be the NASA build plate that we will be provided with, and the gray is our actual build area. Of course, the red dotted lines are the Scout itself inside of the rail system in purple, and everything green is where all of our electronics, electrical components will be stacked up on each other. We know we have about 5.13 inches of height, so we'll use this space to stack PCB boards, IMUs, any other sensors, lipo batteries if we need. Everything will be used in those green areas, including wiring as well. So this is a little bit of the Overwatch system overview. Our main processing power is the Arduino Nano and the Jetson Nano. The Jetson Nano is an IA-based microprocessing, and we will be using this to process our um, cameras, essentially. We want to have a camera at the end of the rail system to kind of capture the moment of Scout deploying into space and kind of track it before it's off out of frame. And then various sensors in suit with the Overwatch would be the RF transmitters, pressure sensors, humidifiers, IMU, of course, the camera, and an onboard SD card to store all data from both Overwatch and Scout itself. Oh, and
Yeah, sorry.
and the actuators and outputs. Um, we will be holding Scout on a multi-point cam, and a whole bunch of servers that would pretty much actuate once we're at apogee level, and have a continuous contact to Scout to kind of top it off until it's I guess deployment.
Okay, then here is a close-up view of what we had here. This is the systems connection system. First, we'll start off with the sounding rocket power. We'll get power from the sounding rocket to the Jetson Nano, and this will have direct control over the Arduino and direct control to the camera. The camera hopefully is to track the Scout once it's deployed. Then the Arduino is going to host all the sensors and radio frequency receivers that we'll have, IMUs, any servos that we're going to use to deploy Scout. And then yeah, it'll also host the SD card on the Overwatch system so that we can have multiple points of data collection.
So let's move on to Scout. Scout is the heart of the scientific experiment. It's a compact, aerodynamically shaped payload designed to be resilient and smart, which means it's very delicate. This is why it's a two-part system within the Overwatch. The Scout itself will have an in-suit of sensors from thermocouples to measure heat, a custom Langmuir probe to measure the electron density as it's descending, and a Raspberry Pi microcontroller to kind of power and control the entire system in an orderly fashion as well. So
Yeah, we also put in a camera here. We weren't too sure if we could do a camera. I mean, we of course we would want to do a camera. It would be really nice to take pictures as we're going down, but we know that transmitting the data wirelessly with such a small like transmitter is very difficult for it to process and transmit pictures. So that's why we decided to move the camera onto Overwatch instead of Scout. But we'll try to do either or both if it's possible.
So this is Scout's components layout. We have in red the transmitter receiver right on top of the Raspberry Pi. We have the SD card mounted onto the Raspberry Pi, a GPS module on the left, an IMU measured unit on the right top corner, multiple LiPo batteries. We want to have them, if we can have them centered or mostly centered, it would be ideal. We won't be able to do it until we start prototyping, and we would definitely add the parachute and the Langmuir probes at the end of the Scout.
Yeah, and that's a basic overview of the component layout for Scout. Obviously, these aren't where they're going to be placed, but this is what we believe we would need on the Scout.
As for a Langmuir probe system overview, so the Langmuir probe is used to measure electron density in the plasma sheath during reentry. We want to have two rod system to mitigate and reduce the marginal error between both rods. And within those rods, we'll have two tungsten wires cased in a metal sphere that allows voltage to pass between the two wires and measure current. All that information will be then sent to our Langmuir probe control module, and it will process this, send it over to the Raspberry Pi, and store it onto the SD card and transmit it over to Overwatch in the intervals of the RF transmitter.
And this is how the Scout system connections. This is the other part to the Overwatch system connections here. So we'll have those two little connectors that we had in Overwatch. We'll have it connected to the battery, so it can constantly charge the battery while it's going up or while it's waiting to be launched. The Scout will consist of a LiPo battery, like we said. It'll consist of the Raspberry Pi Pico, something small but powerful, so we can control all our sensors. It'll host an SD card on board, IMU, thermocouple, barometric altimeter. That is just to measure the altitude that we were at, so we can deploy the parachute at the correct time. You don't want to deploy too early or deploy too late. Then here we have a step-up voltage that goes to the Langmuir probe, as the Langmuir probe requires about 100 to 200 voltages,
Yeah.
I believe. And then we'll have that transmit the data back to the Raspberry Pi Pico to either store it or to send it to the rock block, or send it through the RF transmitter module to send it back to Overwatch. And then here we have the time events from earlier. Time event 1, T minus 100. System on, data recording. Power up the Pico, the Arduino, the Jetson Nano. Start SD logging. Start the camera recording, and then telemetry data, stuff like that. Then T minus 0 is liftoff. Hopefully the IMU can measure all the liftoff data. It'll be like similar to the Rock-On experiment in that sense, where we have IMU on there. Then we have time event 2, which is Scout deployment. This will occur hopefully at apogee once the side skirts are jetsoning off. That will fire the Scout out. It'll unlock the cam, trigger the spring rail system, and turn on the Scout so it can measure its own data. Then further on, there's no really way to get the time event to the parachute from the rocket, but we're going to put a timer on there plus the altimeter so that we can have deployment at the correct time. And then we'll have the camera stop once we reach below a certain voltage so we don't kill the battery too quickly, so we can still transmit data. And then probably before the battery dies, we'll do one big data dump back to the Iridium constellation of satellites so we can see it ourselves. And then we also have a fail-safe stop anytime to abort mission if anything happens, anything gets shorted out, anything goes wrong.
So these are some of the aero mission specs. Overwatch measures in 12 inches diameter and 5.13 inches in height. Our cylindrical volume is about 580 inches cubed, and we're realistically seeing about 70% usable volume area. We want to fit as much as we can on Overwatch since it's our central hub. It should be able to host every single sensor into electronic devices within Overwatch. Our biggest issue would be Scout. Since it's a smaller in dimension and 4.5 inches in diameter and 7.5 inches in length, our volume is about 119 inches cubed. We want to use about 80% of the internal volume, but we'll realistically have around 70% of usable volume within Scout. We also have to include insulation, make sure that the structural can withstand the harsh environments of reentry. So that's why we have a 70% usability of the volume space. We are predicting the weight to be around 10 pounds overall, the entire experiment. We know we need to meet the 15-pound requirement. So if we don't meet the 15-pound requirement, we will be using leaded weights to meet the 15 pounds.
And we'll place those lead weights around so we can get the center of gravity correct, because I know we have to specify that. So here's the user guide compliance. We noted here that the height has to be 5.13 inches or less, and we only get access to half an amp hour, and it has to be within 15 pounds plus or minus half a pound. So center of gravity, we're not sure yet, obviously, because we haven't really made any CAD models or placed anything in specific spots. The weight, we understand. Max height, we understand it's half a deck. Bottom deck has flush mounting hardware. We understand. Within keep out zone, I'm not too sure what that is exactly. So that is one of the questions I have at the very end. Using the GSE lines, yes, we want to power our experiment. We'll be using TE1 and TE2. Redundant power lines, yes. Less than half a milliamp hour, yes. 28 volts, we will have to regulate it down from 28 to the 5 volts so that we can power our Jetson Nano or Arduino. Using RF, we plan on using it. We're not too sure what we would be using exactly, so we can't really give you any specs on how much power output that's going to put out. I know you guys have a max power output for the RF transmitters. And then using a deployable ejectable, yes, we understand that, and we have to be ejected very slowly. And then Holt's team consists of U.S. persons, yes. And then ITAR, that's a bit tricky for us because I understand what it is. I don't really know how to find the list of certified suppliers and stuff like that. Then we move on to our roles and responsibilities. Here is my thing that I made so I can better organize the whole team together. So here we have Hyo-Min Kim. He's our main advisor. He is assigned to oversee us all and make sure that we are in line with the RockSat user guide. He's assistant professor of physics, and he provides scientific guidance throughout the experiment. He reviews our presentations and assists us with data analysis. Then we go on to me. I'm the management project leader. I'm currently a mechanical engineering technology student. I'm getting my bachelor's here at NJIT. I coordinate all the meetings, I manage the Gantt chart, and I make sure that the team leads are doing their jobs and they give us all our deliverables on time. Then we move on to Carlos here. He's also team lead for Scout. He's also a mechanical engineering technology student here at at NJIT. And then this is the rest of our people here. Then we go through here. And then down here we have Sodi Jaskarat. He is another advisor that we have. We have 3 advisors, Hyo-Min Kim, Sodi Jaskarat. Sodi is here to give us his expertise. He has a PhD in aerospace. And then we have Gareth Perry. He's also another assistant professor in physics, just like Hyomin. He will be helping us do the whole experiment. He will give us his expertise. Then we have the team organization flow chart. We have Hyomin at the top. We have the two advisors, and then they go to me as the project manager. I would directly oversee Carlos here and another member that couldn't come today. He had to catch a train. It was the last train of the day. He is in charge. He's a team lead for the Overwatch team, and under him, he has another guy named Thomas Gamer. They will be in charge of Overwatch. And then Carlos Munoz here is in charge of making sure that Scout has their deliverables on time. He has AJ Rembrandt and Aziz Shaikh. We are constantly recruiting new members. This is just the members that are 100% in on RockSat. We believe that we'll have like about 5 more people that are in and out at all times. Like we had people join and leave for other reasons, but then we have people that express a lot of interest. So we have a good amount of people working on this, but not too many where it's too hard to manage or not everybody's like on board. Then for this meeting schedule and communication plan, we meet every week on Wednesdays at 2:30 here in the library at NJIT. We have that posted on our poster that we post on campus for the whole Rocketry Club because we are a subdivision of the Rocketry Club here at NJIT. Then we have bi-weekly mentor check-ins with Hyomin. It's in person. We give him updates on what we've done for the past 2 weeks and what needs to be done. And then here is a link to the shared drive that we all share, that we all work on. We can all work on the CoDR, and we're currently going to start working on the PDR. And then for the communication platform, we use WhatsApp and Discord because most of the students in the school use Discord. I personally never really use Discord. I have WhatsApp, and a lot of other students also use WhatsApp. So we have both, and we post the same announcements to both, and we have group chats and chats that people can join using QR codes if they want to join our team. Then here we have we have the student and mentor work plan. This is just how students will do the work and the faculty will do the work. So for the CoDR here, we're presenting the full conceptual design review of what we think our mission is going to be, all of our finalized experiment objectives, measurement parameters, and preliminary payload concepts. We are defining our mission and goals, developing initial subsystem blocks, diagrams, and assigning preliminary team roles and create the initial Gantt chart. Then for the PDR, we'll create a more detailed version of the CoDR where we finally have our CAD models, our wiring diagrams, and we will start truly picking our components that we think we need and doing a risk assessments on them. Then for the CDR is the critical design review for us. You guys obviously know what it is. We understand that it has to be our full build, like it has to be our full layout for everything. It has to be everything ready so that we can begin construction at the new year once we get back from winter break. Then we go down to the SDR is with our with our prototype, we can start conducting bench tests on all the electronics and begin vibration tests, environmental tests, thermal testing, and we'll document all these test procedures. We know that you guys at NASA like really intensive checklists and procedures, so we will be documenting all of those. And then for the ISTR, similar to the STR, but you guys will send us the mounting hardware and we'll integrate it into that, make sure it all fits, and reconduct all those vibration, environmental, and thermal tests. And then for the SMR, FMSR, we will have basically the full experiment ready. We'll have it launched somewhere. We'll do the full experiment run. And then we move on to the VVC, which is the final visual inspection before we go to before we go to the Wallops Flight Center. So this will be, we know that our experiment works. We have everything's complete. We've done a full simulation of the experiment. And then we'll all package it up really nicely so we can send it, so we can bring it with us to the integration and testing trip. And then once we're at the integration and testing trip, we'll assemble it onto the sounding rocket, and you guys will do your testing and making sure that it passed all tech inspections and stuff like that. Then for the launch trip, we'll be there for the launch. We'll watch the launch, take our pictures and stuff like that, post our socials, and then receive the experiment back to us, do our post-flight mission checklist, make sure that everything is has worked properly, so we can prepare the final report. And throughout all this, our advisors will be there to help us in every way possible and oversee all the test procedures, provide supervision and feedback, and at the very end, give guidance on how to interpretate all the data and publicate it. And then here we have our Gantt chart. This is for me to use to make sure that we were on track with everything. This is just the collapsed version of it. I had to take a screenshot of it to put it in the slides because it wouldn't fit. But here it shows that we completed the IFF form is 100%. That was past due. Then here for the CoDR, this is a little outdated now, but this is at 100% now. And then for the PDR is 0 because we haven't had any of the templates for that yet, so we're not really sure which we would need. And I'm constantly checking this almost every day and making tweaks to it and updating it. So here we go on to the budget that we came up with. Currently, we are picking the half canister, which is a $16,000 fee. Then for materials costs, we are thinking the experiment's going to cost about $5,262. And then for the trip cost, we're thinking it's going to be about $15,000, giving us a grand total of $36,276. I'll be breaking down the materials cost here. For the materials, this is all the materials we think we'll need at the moment, plus some links to where we can buy them and the prices that they are currently. This is constantly changing. We have prototype cost here because we know things can break during prototyping, and we have to make sure that we have the contingency there to be able to buy it. And then we have more testing prototype, and we have testing cost. This was actually brought up to us by the dean of the Newark College of Engineering. He told us that we should add the testing cost because, we need to test like the vibration test. Like they have one here, but in case we need to make something special to it, we can add to that and do some environmental tests. If we need to make any environmental chambers, we can do that with that price. And then we have a contingency, which was also confirmed by the dean to be reasonable. Then we have the trip cost. We know that we have to go in the beginning of June. We are thinking that the hotels are going to cost about $4,284. This is the trip for 6 students and 1 faculty member. Then for the trip 2, which is the launch, we're thinking it's going to be cost $3,500. Same thing, 6 students, 1 faculty member. And then we have food for everybody. And then we have transportation. So we're thinking this is probably going to be the most it could possibly be for transportation. So we're not going to be getting there and scrambling for money or having to make students pay out of pocket for this trip, because we don't want that to happen. Then for the refund policy, Carl's take over again.
As for the refund policy, we, the NJIT team members, acknowledge that the RockSat program fee is non-refundable. We understand that the refund will not be issued under any of the following circumstances. The team is removed from flight manifest due to non-compliance with the RockSat user guide. The experiment fails at a pre-launch delivery or testing benchmark. The experiment is removed from the manifest after integration. The rocket is unable to launch for any reason, and the rocket is not recovered after launch.
Okay, this is for plan for funding. So we've had multiple budget meetings with the Newark College of Engineering. We currently have another meeting set for next week to kind of propose our final budget again. And then we also have reached out to other colleges of NJIT because our team consists of not just engineering students, but like computer science majors and business majors. So we thought, hey, we have their students. Why don't they help us pay for this? Also, we also did speak with the New Jersey Space Grant Consortium. They told us that they possibly have $9,000 in funds for us, as obviously matching that. But we haven't been able to like really get back to them. We've sent them emails, but they haven't really responded to us back recently. And then we've reached out to corporate sponsorships, and we have great news. We have a couple offers already from some corporations that'll give us free products and possibly money. And then we are taking a trip to Valcor at the end of this month with the whole team. We're taking a tour of their facilities, and they make a lot of very sensitive pressure sensors. So that's something we can use on our rocket, on our deployable. And then we also started the application for NJIT Ignite, which is a crowdfunding thing, so we get some funding from around. And that's our plan for funding.
Conclusion, unknowns and worries. We definitely have a lot of unknowns and a lot of worries. The main one being waterproofing and heat resistance for both Overwatch and Scout. We, of course, want both of them to survive the heat and the water from the ocean. Incorporating the camera on Scout is another issue that we are having. Do we have enough space on Scout to actually place a camera within the confined space? Data transmission and reliability between Overwatch and Scout. We are intending to use a long range RF module. Um, Whether it's reliable, where we can get a lot of information within the mission flight, can vary. And of course, testing methods, vibration and vacuum test. I believe we are reaching out to a few other companies that will allow us to use vacuum testing facilities or vibration test facilities as well.
Actually, on that, we did hear back from people in NJIT. They do have vibration testers and vacuum chambers that we can use. So we just got back to them today. Actually, they actually just got back to us today about that. So I didn't have time to put that in the slides, but we do have access to test all these systems. And then, yeah, overall weight of the payload, we're not really too sure how much the weight's going to be. We believe we can make it under 15 pounds and kind of aim for that with the lead weights. And then funding was a big issue at first. It seemed like nobody had money here in the school, but then after meeting with a couple of people, it seemed like the money started kind of appearing once they realized that we were more serious about it, and we showed all of our team organization charts and timelines and stuff like that. And then finally, for the GPS and rock block, we're not sure if we can use GPS. I remember was reading the RockSat C user guide before, because we were planning to do RockSat C, and you guys did not allow any GPS or transmitting dating out of the rocket, I believe. And then I can't seem to find that in the new user guide, so I'm still a little confused about that. And then, yeah, that's our whole presentation. We're excited
Okay.
to and improve our design for the next phase.
Yeah, great. Yeah, leave your slides up and we'll go through some of the questions. But I don't want to qualify my comments by saying this, but well, it's going to sound that way. But for a brand new team that's never done RockSat, you've got a really good start. There are some things you need, let's just say, to better understand how things work so that your next design review captures or communicates that you understand all that. But overall, from a very first step, you've done a good job. And I want to compliment at least the two of you that spoke tonight. You definitely have a lot of motivation and a lot of excitement. At least it comes through to me. And I'm so tempted to not tell you some of the things I want to tell you because I don't want to tap out that motivation, because you don't know what you don't know, and you'll find out, and that'll be part of your learning process. But I hate to also say, yeah, you don't want to touch the stove because it's hot. I want you to, I don't want to have you guys burn yourself, so to speak, but you might prove me wrong and you'll be like, no, I can put my hand on the stove. It doesn't hurt at all. Whatever. Bad examples there. But as far as your last slide here, there's no restrictions on using GPS. There may be more restrictions on the hardware itself that it may not, without it being unlocked or whatever, from a national security standpoint, may not function at a certain altitude or speed. But you can fly one. And as far as a rock block, iridium stuff, you can do that as well. We'll just have to coordinate as part of the normal process the frequency utilization and coordination with wallops and making sure you have all of the right forms completed. So that's not an issue. So I have a long list of things, the suggestions, a few questions. So I want to make sure we can get through it with the time that we have. I think there's a little bit of inconsistency in some of the words you all said and what was on your slides. So I think at one point you said something about an apogee of 250 kilometers or something. I want to make sure you understand. In your slides you show, I think, the correct.
Yeah, it's a
It was 150 to
155.
170
No,
kilometers.
Yeah.
Yeah.
Oh,
Yeah,
Usually it was the time we said by accident.
that's okay. I just want to make sure we're managing the same data or specs, and that could change once we get through our design process, and we'll let you all know. But it sounds like a lot of your success of your mission is getting data from Scout back to you, whether it's through Iridium, which I think is a great idea to have as a backup, and getting a link, RF link, back to the deck. But I will tell you that's it's going to be challenging to do that. You could have a 50-kilometer, as you said, range, but whether or not you can establish a link between that transmitter and a receiver, it's a challenge to do. So just be prepared for some learning there. So I guess my point is that the best thing you can do and should consider doing is deploying earlier than apogee, because your Scout will stay with you as you fly up to apogee, and you'll be able to have more time to establish a link with your system. If you deploy at apogee, everything starts, of course, falling at that point, but you'll have a shorter period of time to establish a link. So it's something to consider in your ConOps.
Okay.
And I hate to burst your bubble, but there's really less than 1% chance you'll ever recover Scout. We've had teams try to recover much larger objects with Iridium, with beacons, with orange paint, much bigger objects than what you're proposing to fly, and they've never been found. And it's hard enough to find the rocket from the air with Iridium trackers built in. So just managing your expectations. I think you could, and then how you get it. If you had an exact location, you'd have to get a boat on your own to get out to 50 miles offshore. And by the time you get there, I mean, whatever, there's just a very, very low chance. So I think you should plan on never seeing it again unless it washes up on shore.
Yeah, for sure. That's why I really mentioned the whole point of like inscribing on the side of it, like a name and address. So it'll be like some sort of like a bottle in the ocean with like a something like that. Something that washes up on shore. Somebody would see it. Hopefully they'll contact us.
Yeah. Well, the main reason I say that is you should fold that into your priorities of what goes in the Scout in terms of, you need to rely on your data, your RF links to get your data, and making those systems more robust than its surviving impact or being watertight, things like that. So, because I just think that you have limited time and resources, you should focus on things that you know for a fact will happen. In this case, you most likely are not going to see it again, and it will likely, whatever. So fins, for example, that may help, but I've seen, the speeds you may reach, I don't think the fins are going to make any difference. And you would need a lot more weight, especially in the nose of your system, to make sure that it's always pointed down for those fins to probably have an effect. I'm not saying it won't, but again, you're trying to, well, I don't know. I think you have to do some analysis on how big of a fin you would actually need to, and it may prove that it's too big for you even to fit with your weight and all that kind of stuff. So as a little bit of education, make sure you understand that your deployment has to be mechanically restrained before launch. So you have a timer event which it looks great that you did that because that's required as well to actually conduct the deployment. So when you get that timer event, it triggers something in your electronics to deploy, but you need like a servo, or some sort of physical mechanical thing that's holding Scout back prior to that TE event happening. And it can't be just like a wire, a burn wire. You know, it's got to be something solid. So we can talk more about that, but that needs to be part of your design, how you restrain it so it doesn't come out when you don't want it to.
Yeah, we had like a multi-cam system that would like lock in. We mentioned that in the slides, but I don't know if it really translated through the presentation.
Yeah, well, yeah. I mean, it's early on, but
yeah,
eventually you're going to want to show what that design is. And we'll, again, our goal is to have you be successful, but also not cause the skirt of the rocket to come off or not come off because your Scout is jammed up against it because it vibrated out of its cam system.
Yeah.
Let's see. Let's see. You have a lot of stuff going on in Scout. This is one of my comments that I'm like, do I make this comment or not? I mean, I think you have so many things you're trying to do within that Scout that I worry that it'll implode under the weight of what you're trying to accomplish. And so if you were my students, I would be suggesting you come up with some very core sensors or core items. For example, you're still debating whether about having a camera, and what are the 3 things you really want to do within that deployment space coming back, and nail those 3 things, get them to work as your baseline mission. And then if you have time and you have the ability to add in additional sensors, you can do that. But I worry that that is a lot to try to accomplish in a deployment. Most student deployments, they do 1 or 2 things because they're challenging enough to get the RF link back, and you can only push so much data through that RF link anyways.
Yeah.
Spend all your time trying to do 5 or 12 sensors, and then you find out, oh yeah, we get 1 data packet every 2 minutes because we got too much we're trying to transmit. So my advice is, I would consider you should consider focusing what you do within Scout so that it's simpler, it's more robust, and you're going to be able to achieve more through that process. Not saying you have to, just
Yeah.
What actually ejects your parachute? You said you had an altimeter, but what is the mechanical thing that pushes out the parachute? Do you know?
It would be another spring-loaded system to kind of pop out the first tiny parachute and to expand into the secondary bigger parachute.
Yeah, but you would need something that's holding that spring shut. Is that going to be a servo or
back servo probably?
Yeah, if you don't know, that's fine, but
yeah,
you're going to have to figure that out. So I mean, that's even another system within Scout that. And then maybe you don't want a parachute. If you decide that this is a sacrificial probe, and you need to descope something, you're going to say, yeah, it's going to hit the ground at a terminal velocity or hit the water, but we know we're not going to get it back, so let's not even worry about a chute. So something to consider.
Okay.
And how does Scout get powered on? I see you have a battery, but what turns it on? Because it shouldn't be running on the battery prior to ejection. At least that's my understanding.
Here we had a quick contacts. We've seen other students, like other teams, use contacts there, and it'll like kind of just once it comes out, it'll like pop out.
Yeah, it'll just start.
It'll be like maybe like a watch thing, where it just sticks on.
Okay, yeah, and I think I have a specific comment for you that your functional block diagram needs a little bit more detail, and it should be on its own slide with both of your systems. So in this case, the contacts would help us understand that, I know you got a line going there, but what we want to see, a functional block diagram that we like to see encompasses everything that happens on your system on one slide. So the examples that we included in the template show an entire experiment all on one slide. And you know, you have, if you go back to your other one, you have the famous miracle happens here box, so to speak. So you got timer event 1 directly going into your Arduino, which I don't know of any Arduino that can handle 28 volts. So there's a function in your system that's missing, and you referred to it somewhere as a power board, but you need to
Yeah.
show that functionality on your functional block diagram as well. Same for your Jetson.
Okay. Yeah. Yeah. I do remember mentioning that we need to bring it down to 5 volts here.
Yeah,
Yeah.
yeah.
Okay. Yeah.
So my advice is to, and again, you're new to all this,
Hmm.
so that's fine, but I want you to be successful. So look at some of those examples. You're on the right path, but your functional block diagram is what I like to say. You can explain it to anyone, and they know how your system functions, how it interfaces to the rocket. You can show it to the dean, or you can show it to your mom. Either one will be able to understand the functionality in one slide of how everything works. So I'll harp on that a lot if we continue working together. So it's a good start though. What's your anticipated injection speed? You know, you have it here on this slide that you're going to be 1 inch per second. We can approve higher speeds, but what's actually ejecting Scout is another question. So is it a spring? Is it, you know, you've talked about how you might restrain it, but do you plan to push it out with a spring or a pusher plate or?
We are planning to use a spring to kind of push it out, and it would be on a rail system, so it doesn't deviate either
Yeah.
direction.
Okay.
So just be on a rail, pushed out on a spring. Pretty much, that's the
So,
deployment sequence.
yeah. So at some point, as that design matures, you're going to have to do some estimate on the stored energy behind that spring, how fast that's going to eject, and depending on if you're like, oh, you know, gosh, this is going to be 4 inches per second, then Wallops will probably ask you to do sort of a simple energy calculation. You know, I have examples I can give you, but the main thing is that you need to be thinking about designing that as part of Scout as well, or your Overwatch.
Okay.
And on this slide, you talk about ITAR. Not sure what that means. Basically, if you buy a piece of hardware that says it's ITAR, then we have some concerns about that. So, or if a company, which you've already mentioned, some companies want to provide you some hardware or sponsorship through that. If a
Mhm.
company comes, yeah, here's your pressure sensor, but it's ITAR restricted, you can't share any information about it, no pictures, whatever, then that's a no-go because it has to be completely open source, so to speak.
I see what
And
it.
Oh, okay. Okay.
we
That
can't
was.
be responsible for a student coming up and taking a picture of something on your experiment that's not supposed to have a picture taken of it.
Okay, because I thought for a second maybe that you wanted us to use ITAR.
Oh no.
And I was like, wait, that's really difficult. Like,
Yeah, no, it's just the opposite.
okay,
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 perfect.
perfect.
You also had a keep out zone question. So if you look at the user guide, there's the full plate, which has got a diameter, and then there's a line around that in the user guide that you kind of have it right there. So
Yeah, I think that's the keep out
Okay,
area.
that's the
Yeah.
keep out zones.
Yeah.
Okay, okay.
yeah, so you don't want to
Yeah.
get into that outer. It's this line actually. If you I'll go
Oh,
back to that previous. Yeah. So it's this line right here. Oops, not a very good circle, but if you get into this space, you're in the keep out zone. So right now you're within the keep out zone, so great. No worries.
got it. Okay.
If you decide you need to be in the keep out zone, like you want to scout right up to the edge, we can talk about that. But
Okay.
um,
I'm gonna go back to the last slide.
no, it's fine.
Okay.
On your budget, you talked about the power board, so that's what, or I'm sorry, user guide matrix, you talked about the power board there, but I didn't see it anywhere else. So it's just again part of that functionality of how your system's going to work. And to be clear, on your budget, you refer to a canister. You know, this new program is just those decks. So just making sure you got that. I think you do because you're showing the Carol section and all that. I do want you to know that most teams don't vibration test and they don't do vacuum tests. Doesn't mean you don't have to, but I don't want you to stress about, oh my God, we have to do a vibration test. Most of the time, students who build with, a level of mechanical common sense, they're not using 3D printed materials, which we would not allow, but, general good design, which we'll also kind of evaluate with you, a lot of times will be just fine during our vibration tests. You have bigger problems with when it comes to electronics, things like that, how you might solder a MOSFET sticking up off a board or something like that. But if you do have the access to test vibration, great. Same with vacuum testing, but all I would say is be very careful you do it right and you don't over test it. If you vibe it at a much higher level than we're going to do and it breaks, then that was an over test. So
Yeah, I mentioned it because they said that they did have it. So I was like, oh, okay, okay. So it's good to know that we have it and that we can use it.
yeah, but if you find out, oh my gosh, yeah, we can't vibe a 15-pound experiment, we can do boards. Well, then do boards and things like that. But a lot of teams don't vibrate before they come to wall-ups.
Okay.
And if you do and you succeed, then you're going to be just fine. But that's a lot. So that's a lot of things to cover. I'm trying to see if I missed anything. Yeah, Wesley, do you have anything else? I know we're a little over time here.
Yeah, no worries. Yeah, no, I just definitely a lot of good information coming out coming out of what you have. It's an excellent start, and I think it puts you into a good position with the things that Chris has mentioned as well, just to kind of keep you in those guide rails. But I really don't have anything else that hasn't been mentioned.
Okay.
I don't know if you're able to find what you're looking for.
Just, I think you two are very motivated. You have on your org chart, you have other students who did not present tonight, which we'd like for you to have as many of your team present. But the main thing is that you have active team members beyond the two of you. So that looks like you do have that. So, teams of two don't usually survive. So
Yeah, for sure.
you have a team of looks like about 6 plus some other advisors. So yeah, I'm glad to see that.
But the more the merrier.
Thank you. Thank you. Yeah.
We're constantly recruiting.
Yeah,
and doing
we're
events
constantly-
and stuff like that.
Okay.
Yeah.
All right. Do you have any follow-ups from all the questions we asked or comments we made?
As of right now.
Yes, just one for the funding. How do we get in touch with the space grant? Because we've emailed them a couple of times and we've actually set up meetings. We had meetings with them, but they kind of left us on red and haven't reached back to us. So if there's any way to help us with that.
Yeah, I can't technically. I mean, I don't have any pull or connection to the New Jersey Space Grant, and they have no obligation, obviously, to fund you. But I would just be persistent, whether it was Space Grant or someone else who said they would meet with you. Try calling them, try, I don't know if it's a drivable distance to go knock on their door. I know that they also support the Stevens Institute of Technology RockSat team, so they could be getting confused with that, perhaps.
We met with both of them, actually.
What's that?
We've met with both.
Yeah, we met with
We met
both.
in one meeting with both Stevens and the Space Grant Consortium. So
they're
hopefully
they're ghosting you, I guess.
I guess so.
Yeah, just a little bit.
Well, that might be a role where your faculty advisor could advocate. I don't know if I want to make sure I'm saying this right. Is it human?
Yes, human. Yes.
If you have any connections, sometimes they have a harder time ignoring faculty versus students, but or include him on your emails to Space Grant. But you should not. They're not by no means obligated to fund you, and I don't want you to say, Chris said you'd fund me. That's not, I won't go over well. But you can ask and they can say no, or they could say yes. But it seems like you have a lot of good ideas for getting funding beyond that. So, I'd encourage you, don't let their no turn you away from trying other things, but it wouldn't hurt to keep bugging them.
Yeah.
Yeah, definitely.
Yeah, let's chat about this funding opportunity later.
Okay. Well, we're over time, but I do want to set up your PDR time, and we have to do our famous screenshot of the team here today. So let's do that now. If you want to be in the picture, you can turn your camera on. If you don't, that's fine. But we just use this for our note page, and then so here we go. 3, 2, 1. Got it. And oops. It did not work. There he goes.
Outside.
Is this your preferred time, like really late at night on a Tuesday?
Let me think. Well, you have work, and I have work on Fridays. So
Wednesdays are our most preferred time around, well, actually every other Wednesday.
Yeah.
Because we have
this
one
time
class.
for sure is a time that we could do, but
What's that? I'm sorry.
I said this time is like a for sure time that we could do. So
Okay. Yeah, I mean, it seems something about New Jersey teams. The Stevens team does the same thing. Like theirs is tomorrow night at 9:15 Eastern, which just surprises me. But so you're the only two teams that want to meet late, which is fine. We can do that. I just want to make sure that there's no other options. And if there isn't, that's fine. And we will continue to meet, at least for PDR, at this same time and day, perhaps, because I think Wednesdays the Stevens team has that. But you said, yeah.
So we have availability for every other Wednesday. So not this Wednesday, but next Wednesday we will be available. So when does the actual
yeah,
So
we're probably in
it's supposed to be the week of the 17th of November.
on, off, on
So I think that would translate to the 25th.
25th, right before Thanksgiving, or the week of.
It would be
Yeah.
Or sorry, the 26th. I'm sorry.
Okay, so
We
26.
can do that,
Yeah, we should be free that Wednesday.
1 second. Somebody text.
Yeah, that is the Wednesday night before Thanksgiving. So I don't know if that's a factor to you guys.
Yeah.
Or we could do Tuesday night, the 25th, or Tuesday, the 18th, perhaps, which is the week before.
Let's see that. Give me 1 second. Sorry. This schedule with our class every other Wednesday we meet. So
You said Tuesday. We don't meet on Tuesdays.
we don't meet Tuesday.
We can do Tuesday or Wednesday.
That Wednesday, the 19th, we do have class, and then the 26th we don't.
Okay, that's
So
fine.
we can do the 26th.
We can do the 26th at an earlier time too.
Yeah.
We can do
Oh,
26 at like 6. Actually, 6:30.
If that's fine with you, is that fine with you?
Yeah, I'll try to make it happen.
So when you say 6:30, are you talking Eastern time?
Eastern time.
Okay, that's nice. Okay, so that'll be 4:30 our time on the 26th. And let me just. Okay, great. Got that recorded.
Okay.
All right. Well, it was really nice to see you all again, and great work on your first review. And again, we'll send out some detailed action items next week for everybody.
Oh,
Thank
I
you
mean,
so
thank you for this flexibility, Chris and Wesley. I was also surprised to see this like unusual time because I thought this is what you actually scheduled, but turns out that our students actually bothered you.
Oh, that's we yeah, no, we try to be as accommodating as possible, especially when we have 24 teams we're trying to schedule.
Mhm.
So if we tried to do it on our schedule
Yeah.
of a normal business day, we wouldn't be able to do it. So I'm glad it worked out. So
Yep. Thank you very much. Yep.
all right. You have a great evening, everyone.
You
Okay.
too.
Hey, you
All
too.
right.
Thank you,
See you.
Dylan.
Have a good evening.
Bye-bye.
See you.
Bye.